Good evening. Hello. Am I audible? Hello. 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 Am I audible? Shall we start the session?
Yes.
So, myself, Manjunathan. I am a research scholar from Department of Applied Mechanics in IIT Madras. So, this is our live interaction session for our NPTEL course, Biomechanics, by Professor Varadhan. I hope you have already gone through the session, I mean, the videos. Uh,
Yes, sir.
Sorry. Okay. So, I will just start with what's the course content, and how to go forward. So, uh, hope everyone can see this see the screen. Is the screen visible?
Yes, sir.
Okay, so this is a basic introductory course to biomechanics, and in this course, this we are not going into much deeper contents, but kind of covering basics plus mm, intermediary levels only. So we will start from the basics of mechanics, mostly how human body, the forces acting on the human body, how the human body can support itself. All those things are being discussed in this course. Uh, so, as the course name itself, Bio plus Mechanics, that is how the mechanics principles of mechanics can be used in uh, human body or human physiology, and how the anatomy is being analyzed with the use of mechanical principles or principles of mechanics. So I hope everybody almost everyone have gone through the week 1 courses. It is just some introductory mechanics course only. So I hope in at least in school level courses or plus 2 level courses, most of you got covered these concepts of mechanics, like uh, what is statics, what is dynamics, and all those things. So basically, uh, week 1 is kind of a refresher for all those basic principles, so that because only if the basics are good, then only we can go for the complex uh, mechanical calculations. So in week 1, if you have seen the videos, mostly the uh, contents related to forces and transmission principles, all those things are discussed in details. And in week 2, how these principles of mechanics can be brought into a human body, that is human body as a biomechanical system. As we know, force is not developed as such in the human body. It needs to be some chemical reactions are there, then it is went to the this energy is being transmitted to muscles, and the muscles is kind of converting this chemical energy into mechanical energy. Then only the force develops. So how that force acting on particular muscles and other connective tissue helps the organs or limbs to move, that is being discussed in week 2. And in third week, it's like what I already told before, how this force production is happening in skeletal muscles. Even though there are, I told muscles, there are different types of muscles, and uh, particularly skeletal muscles. That is, skeletal itself is meaning giving shape. So the muscles that is giving shape or rigidity to the body, that is called skeletal muscles, and how the force is being produced in the skeletal muscles. When these particular uh, chemical or particular some particular ions and chemicals are reaching our muscles, how it is being converted to the force. For that, there are different theories. One of them is called sliding filament theory. How these filaments of the skeletal muscles are sliding over each other, and how the contraction and extension of these muscles develop force. So that is what we discussed in the third week. And then in fourth week, we will be concentrating, the course videos are being concentrated on how the joints of the upper limb can be analyzed using our laws of mechanics. Upper limb means mostly our hands. So if hand, when when we say human hand, it mostly consists of starts from the shoulder. Uh, it is then goes to the other joint is elbow, wrist, hand, and fingers. This is the set of the entire set of human upper limb or hand. So these, if you see, here are shoulder is one joint, elbow is one joint, wrist is one joint, and there is hand. Hand is actually uh, made of multiple bones, small bones interconnected with each other, and also fingers are also small pieces of bones that is being connected to each other. So how these, if you are aware of mechanical terminologies, something one bone, suppose I am drawing here, suppose this is shoulder, this is elbow, this is wrist. So these bones becomes, the bonds between these becomes act as like links in mechanical. So one rigid part. That's how we are kind of uh, conceptualizing in biomechanics. So how these particular links can move with respect to the joints. So here the joints are in shoulder, elbow, wrist, etc. So there are something called degrees of freedom. Here, our shoulder joint or elbow joint don't have any translation degrees of freedom, but mostly uh, rotational degrees. So, how rotation of one particular joint uh, is affecting the motion of the preceding link, sorry, the succeeding link. That's how we will be analyzing joints of upper limb. Then in week 5, other than that, there are different kinds of joints. So just if you see shoulder, it's kind of a ball and socket joint. It has it has much more rotational degrees. Uh, but however, the other joints like spine, hip, knee, and ankle has not much degrees of rotation. It is kind of limited. So all those joints are being analyzed in week 5. And in week 6, I already told you it's kind of a multi-link chain. Here you can say there are multiple bonds joined with some particular joints. If we in mechanical engineering, it will be called like linkages. So one particular bone is linked to another bone by particular joint. So, and how the relative motion happening between this one and two bonds will be entirely decided by this joint, that is degrees of freedom provided by this particular joint. So if there is multiple linkages, and how one motion started from the first link is being propagated to last link, that is kind of difficult problem to calculate. So for that, some particular approaches are there. So uh, if again, if we are assuming our upper limb as a linkage uh, or multi-link serial chain, that's being told as here. Multi-link serial, because I already told you this, like there are we have this bone from shoulder, one bone is there, then elbow, another bone is there, not one bone, two bones are there. Then again, wrist, there are multiple bonds going towards fingers. So all these linkages are there. And how one particular motion, suppose we can think in two way. Suppose if I say this is shoulder and this is finger, so how one motion starting from this shoulder is being transmitted to finger. Suppose I am rotating shoulder by some degree in one direction, then what will be the movement of one particular finger, suppose index finger. So that is propagation. So this propagation of motion, how we can calculate that? That one is called forward kinematics. And suppose we need some particular motion at the fingertip, so that we want to move our finger and touch one particular object. Then what should be the force or degrees of rotation that should be done by the shoulder? That's we are kind of backward calculating. First is that, but suppose shoulder is moving by some value, some value of rotation or degree, then what will be the result of finger motion? That is kind of forward kinematics. We know what is happening in shoulder, and relatively how it will be transmitted to the other joints and linkages, and what will be the motion at the fingertip. That calculating that is called forward kinematics. Suppose we have a determined motion. Mostly we think like that. We want to move our finger and touch one particular object. Then how all other elbows should be moved. So that is called inverse kinematics. These are two things. And there is one system called dynamic Hartenberg, that is called DH. So how this that is one simple formulation developed by two mechanical engineers called Dynamit and Hartenberg, and they have created that system. And this is kind of widely used in our pick and place robot, and also because if you have uh, learned about this industrial revolution and all, uh, some 40 years back, there was kind of very huge revolutionary changes came into the industries because of these pick and place robots or robotic arms. So even if you have seen, you might have seen some videos of large robotic hands are picking and moving large objects, like in production chain. Suppose we have one uh, manufacturing unit. We are manufacturing cars, and this is a large body. We have to pick up every part of a car and dip it in some paint or something. So that will be done by some mechanical amps. So how that motions can be uh, carried out by that particular mechanical arms. We have to calculate that. That's called path planning and all, because there will be humans working in between. So there should be no human machine conflict, all such things. So this path planning and minimal energy. We have to spend minimal energy to move some object. So that again comes into picture. All those things can be calculated using this DH parameters, and these two things called forward kinematics and inverse kinematics. And then moving on to mechanics of week 7, that is mechanics of hard tissue, where in human body the links, as we call in mechanical engineering, is bones. The bones are the part of our body which gives proper structure to the body. So how the body is constructed, how what is the structure of the bone, and how the bone is being kind of uh, better than one particular mechanical link or piece of metal. Why the bone behaved in this particular manner? Because every biological tissue or every material has its own properties that is well suited for its function. So week 7 discuss much deeper about the microstructure of the bone, and how uh, and why that particular property of bone exists, and what are the advantages and disadvantages of that particular composition. So all those things are being discussed in week 7 lectures. Then moving on to week 8, there will be discussion about the discussion is on entirely on soft tissues. So this the structure of a human body is provided by bones, but we need soft tissues. We have soft tissues covering it, and soft tissues are needed for the proper functioning of the bones or proper functioning of the organs and limbs. And these soft tissues have again different properties. There is something called viscoelasticity. That is, viscosity and elasticity is a combined term. So I already have might have learned about elastic properties and plastic properties. So there are some materials when some force is applied on it, it will stretch or it will deform. But once the force is removed, it will regain its original structure. Such materials are called elastic materials. If that force is kind of permanently deform that materials, then it is called plastic material. So these two are plastic and elastic materials. And again, there are different levels of plasticity and elasticity. And mostly we have studied about linear elastic materials, but our soft tissues like muscles, uh, endothelium, skin, everything has some other all these things falls into entirely different categories called viscoelasticity or viscoelastic materials. So how this property of how this viscoelastic material of soft tissue is helping the movements. That's what we will be learning in week 8. Then in week 9 there will be discussions on different types of soft tissues, that is cartilages, ligaments and tendons, etc., and how the stress strain relationship. Again, uh, you might have learned about this stress strain relationship of elastic materials, how elastic material is having some Hooke's law, and possibly many people might have studied stress strain relationship. So how the elastic material will behave and plastic material will be behaving under force, that is kind of stress strain relationship, and how the stress strain relationship of these particular soft tissues vary with each other, and how is that particular property is helping the human body. All these things are discussed in week 9. And also due to the particular properties, this will be having some I can't say some negative um, properties, or we can say something like limitations. That is what gliding resistance, tendon wrapping, and enslaving kind of things. So this is kind of limitations of these particular soft tissues due to their own properties. All those things will be discussed in week 9 lecture. And in week 10 it is called enslavement. So enslavement is something we all have seen from our very childhood, but we never cared about that. So if you can try moving your you can stretch out your hands now and try moving index finger only. You can see other two or three finger will be moving with that. So that if you are only trying to move only one finger, the other fingers are being affected. Or we can say the moving finger is kind of dragging the others with it. So this is something called enslavement. So how one finger can uh, develop this enslaving to other uh, uh, fingers which are near to it. So this is what called enslavement, and how the rest posture, and also how which finger has dominance over other fingers. All those things will be discussed in week 10 with the help of some research papers from Professor Vardhan's research. Then in week 11, uh, the orientation of 3D space, because I already told you the hand or upper limb. If I am taking a example of upper limb, this is kind of moving in a 3D space. So how one particular motion can be defined, because motion as such needs to be quantified in two ways. One, we have to quantify the scalar quantity, how fast it is moving. The velocity, the speed, or something like that should be mentioned. Also, the direction in which it is moving. So, all those things, when it comes to 3D space, it becomes complicated. So, to simplify that, there is something called rotation metrics. And these rotation metrics, actually, we will be discussing these rotation matrices much earlier in DH system itself, and how we can use these rotation metrics to predict the relative motion and relative orientation of the linkages is being discussed in week 11. And again, in week 12 is about some practical application and limitation of these mechanical theories, and also an introduction to stability and gait analysis. Gait is kind of posture. If you might have seen, one particular person will be walking in one way, one style, one particular way of walking will be there. So all those things kind of falls into something called gait. So that will be, there will be a small introduction about that also. So this is the overall course contents. These are some books and references given in the lecture in course itself. So these kind of these texts are mostly available in internet and all. You can kind of Google it and the PDF will be available. So if anybody wants to start with, uh, I would suggest start with this basic biomechanics by Susan Hall. So this is kind of this starts from basic, and it will kind of introductory or basic friendly text, and most of the things what is being discussed in the course will only be there in the exam. So this is most of the other texts are kind of from for your additional knowledge or deeper knowledge. Hope uh, any doubt, or is there any doubt or anything to ask? Okay, so in week one video lectures, uh, these topics are being discussed. That is how uh, mechanics can be applied on a body, and what are the types of forces, and basic principles like principle of transmissibility, the solving of forces, and with some examples. These are being what is being covered in week one lectures. If anybody is left to watch the videos, please watch the video and do the assignments. So from mechanics or mechanical point of view, force is something, or force is an external agent which is capable of changing a body's state of rest or motion. So this is the definition for force. And also force is a vector, that is force has magnitude as well as direction. And some simple terms or simple types of forces what we will be dealing in this course is called applied force. That is which the force that is being applied externally or internally to that particular link or bond or something like that. That is applied force. And is the other thing is reaction force, which will be equal and opposite to the applied force. Developing or trying to oppose the applied force is called reaction force. Spring force is everybody knows what's a spring, and when the force is being applied to a spring, it will store it, and it will, once and when the force is removed, it will be giving or what it will be giving back that stored force. That's something called spring force. Gravitational force is the force of attraction due to the gravity. Friction force is the force due to the surface roughness. One particular uh, principle that is being used as taken as granted in mechanics is called principle of transmissibility. That is, a force can be moved along the line of action. Suppose this is a body, this block is a body, and the this particular red arrow is a force being applied to it, and this red line is the line of action of the force. So, principle of transmissibility of forces says that this particular force can be moved anywhere along this line, that is the line of action of the force, without changing the external reaction on a rigid body. So we can move this force anywhere along this line of action without having any consequences. That is called principle of transmissibility of forces. This particular principle is there only to simplify the analysis of rigid bodies, so that we can some particulars say these there is some other force acting on the body. So I can just move these two forces to create one resultant force. I can just move this vector to connect here, or I can move the force F here to get a resultant. So that is so that I can move anywhere. We can move this force here, these two forces to here, to construct a vector triangle or vector addition. Are all those things exist because only because of this principle called principle of transmissibility. And the other thing is like we can resolve mostly to simplify the forces. So forces will be in arbitrary. When we are talking about 3D space or even 2D space, the force may not be aligning with the Cartesian coordinates or the what is x and y coordinates. So suppose if you look here, this particular force is kind of inclined to both x and y axis. So for simplifying and for the computational analysis, we can just resolve the forces in the direction of the Cartesian coordinates or the which are the coordinate system we are using. So such a method is called solving of forces. So if you see here, the force F is denoted by this red arrow, and this is kind of tilted by theta degree with x-axis. So we can create two other vectors OA and OB as component of uh, these force and angle. And for simplicity, you can keep in mind that whichever component is making the angle with that particular vector, that is where the angle is situated, that particular component will be cos theta. So this f of x will be f cos theta, and the opposite side, opposite one will be sine of this particular component of this particular angle. So fy will be f sine theta. So wherever the angle is being made, that particular component will be cos component. So in our introduction sections, I don't know who all have done this particular course before. I mean, not this particular, any NPTEL course before. In our live interaction session, it will be like you have some assignments every week. So in our interaction session, we will be discussing some similar questions, not the exact ones. I can't help you with the actual assignment questions, but uh, we will be discussing some similar questions that will help you work out the assignment questions. And to make it interactive, I will just read out the question, give some seconds of time. You can just inbox the answers so that we can keep it interactive. And also, don't hesitate uh, to ask doubts. Okay. Anybody have a doubt? I see a raised hand. Any doubt?
No doubt, sir.
Okay. So please try to interact, try to answer the questions. Uh, don't feel bad to give if the answer is bad. So you will be benefited in the exam actually. Most of the questions we will be discussing will be either similar to the assignment questions or some previous year questions. So first question is force is a vector, true or false?
Yes, sir. True.
Uh, please inbox your answers. Yes, we have already discussed that's few minutes before. Force is a vector because that force is being represented by some quantity, that is magnitude, and direction. So we need these two things to completely specify some force. So how much the force actually, uh, what is the quantity of that force, also in which direction it is acting. Also with the Newtonian definition of force, that is F is equal to ma. Here force is made of two components where mass is a scalar and acceleration is a vector. So from with that itself, you can say force has both magnitude and direction. So next question, which among the following can be zero when a particle is in motion for some time? So the question is, which among the following can be zero? Meaning, which of the following options can become zero when a particle is in motion for some time? Options are option A, speed, option B, force, option C, time, option D, displacement. You can inbox your answers. most of you have learned like displacement D. Okay, this is some thing tricky when you are attending. If you are attending the exams, uh, do try. This is actually on previous year question only. Do try to check whether the question has multiple answers, so that you can just try to click multiple. If you have some doubts, try to click on multiple options. If the answer is taking multiple options, so here we have two answers, that is displacement as well as force can be zero when the particle, suppose the force is acting uh, uh, one particular uh, suppose take a pendulum. uh, so first I am just giving it a force. I am trying to push it one side and leaving it. It is kind of oscillating. So I am only giving it force initially only. Then after that, it can come to uh, a point where the displacement is zero as well as the force is zero. So these are two vector quantities which can become zero after a particle in motion. So it's an open-ended question. So whenever you have some doubt, it's an open-ended question or multiple answers can be there. Try to click on multiple options and check whether the question is accepting it. It is a computer-based exam, so try to check that. Uh, the, there won't be any specific mention for that. Only from the question you have to find it. Okay, moving on to next question. What is the SI unit of force? So, first of all, what is SI? Yes, most of you are right. The SI unit of force is N. N stands for Newton. So, Newton is the SI unit or System International Unit of Force. And also here, if you see, the kg is wrong. K should be small. All other properties are capital letters, but K should be small here. Next question. Shoulder joint is an example of hinge joint. Options are option A, true, option B, false. So the question is, uh, shoulder joint is a hinge joint. So then if not shoulder joint is not a hinge joint, then what is most of you have answered false. Then can you say what kind of joint is our shoulder joint? Yes, ball and socket. So there are different joints type. One is pivot joint. This I am writing from types of synovial joint or anatomical joints. There are mainly six types of synovial joint. One is pivot joint. Second, hinge joint. Then saddle joint. This we will be learning in coming lectures, but I'm just telling you now. Condyloid joint. Fifth one, plane joint. Sixth one, ball and socket joint. So for ball and socket, I have told shoulder joint. So can you say any example for pivot joint in human body? Yes, neck is an example for pivot joint. Pivot joint simply says if there's one structure, then we can just move around. This kind of motions are possible. Then it is called a pivot joint. So next one, hinge joint. Can you give me an example for hinge joint in human body? Yes, knee and elbow both can be said to example for hinge joint. Hinge joint, from the name itself, it's simple to understand. It's like it acts like a hinge. So these are two linkages. It uh, can open to its maximum plane of action. So that is called hinge joint, or sometimes called as book joint. Book joint, like similar to a book, so it's called book joint also. Then saddle joint. So can you give me an example for saddle joint in human body? Metacarpal, thumb, finger. Okay. Any other example? Okay, not just thumb or metacarpal. In heel also, uh, CMC, CMC joint also heel as saddle joints. So saddle is like if you think of a horse saddle and one person sitting above that. So that is particular motion. So that this is kind of shape. So both can move, both joints can move around these directions. So that is what saddle joint is. So next one is condyloid joint. Can you give example for condyloid joint? Okay. Uh, wrist is an example for condyloid joint. This also have other name as ellipsoid joint because the movement, the rotation plane is creates an ellipsoid. So that's why it's called ellipsoid joint. And these condyloid joints, if you see, it will provide motion in two planes. And next one is plane joint. So one more example for plane joint. Then we can move on to next question. Yes, ankle. Ankle is plane joint. That is our our leg is kind of coming down like this, and this is our foot, and it can rotate in these ways. So in a planar motion, that's why it's called plane joint. So these are main synovial joints in our body, and shoulder joint is a ball and socket joint, not a hinge joint. Moving on to next question. Resolve the force along x and y direction. We have two diagrams. So just resolve these things. I will just keep A, B, C. So if you can put answer for what is this A, B, and C, I'll give 2 minutes. Try to answer. Oh, sorry. Try to solve the force F, B, and C. Uh, is this only for direction, 30 degrees only for direction. Our force is F. Try to solve in B and C direction. No answers. So let's break it down. So suppose this I am taking this force out. This is force F, that is 10 Newton, and I want to find the x and y components of this force. So take it Fx and Fy. Fx is B and Fy is C. So first thing, where is the angle located? We have already discussed. If the angle is located, then that component becomes cos component. So here the force is the angle is given at here. The F force F is making an angle 20 degree with the rod or this particular component. So this is 20 degree. So is this the theta of rotation with x or y? No, no. It is only this is the angle between the force vector F and the axis of rod, but it is not the absolute angle between horizontal or vertical. So to get absolute angle with horizontal, we have to add these two because this particular rod is tilted at 30 degree. Then this force vector is tilted again 20 degree. So total theta will be 30 plus 20, that is 50 degrees. Then here it is 50 degree. Then f of x, that is b, is equal to f of x becomes f cos 50. F of y becomes f sin 50. So can you calculate this and say what is the value of b and c? That is f cos 50 and f sin 50. Am I audible? Hello? If anybody has any difficulty or doubt, please don't hesitate to ask. Okay, I hope everybody understood the question. The question is resolve the forces along x and y direction, and here uh, I asked you to resolve this force F. So here we need vector and force vector F and also the direction of rotation or direction of inclination. So for that the question is given, the angle is given in two steps, that is the rod is rotated at 30° and force again is rotated at 20° from the rod. So the total angle of rotation of the force with respect to horizontal becomes angle with respect to x direction becomes theta, that is 30° plus 20°, that is 50°, and we have already discussed that the component of force which includes the angle of rotation becomes the cos component. So f of x is f cos 50 and f of y is f sin 50. So you can calculate the answers. Yes, yes, yes. F of x is 6.43 and f of y is 7.66 Newton. So these kind of questions you can expect for exam also, and you should have the presence of mind. You should not go with the 20° as such. So you might be uh, jumping to calculate f cos 20 or f sin 20, then your answers will be wrong, and obviously that options will be there in the options also. So these are kind of trying to check your presence of mind. That kind of questions you can expect for exams. And this is one simple linkage. There will be multiple linkage with this kind of twist. Next question is, scissors are which type of lever? So you have these lever principles and all we all have studied in school itself. So there are three type of levers. So in which type of the lever scissor is an example? Option A, class 1 lever. Option B, class 2 lever. Option C, class 3 lever. Option D, do not fall in any class of lever. Try to answer the question. Okay, yeah, class 1. So how these levers are classified? Uh, these lever systems are kind of defined to is what reduce the effort we are putting for do some work. So there are three things called fulcrum, load, and effort. So the our always our objective is to reduce the effort to move the load, and there is something in between called fulcrum. So if the arrangement is like EFL or LFE, that is fulcrum is in the middle, then that type of levers are known as class 1 levers. So in scissors, it's like our load will be at the end, effort will be given at the other end, and fulcrum is in the middle. So this is a type of class 1 lever system. Moving on to next question. This may not be have in the videos, but try to answer the question. The primary function of tendons are. So we have already discussed what is muscles and skeletal muscles. So this I have not discussed in our introduction section also. So, but you might have studied in the school, and also you might know what's a tendon. So try to answer what's the primary function of a tendon. Options are: option A, to conduct action potential; option B, to attach to bones; option C, to attach muscle to bones; option D, to produce movement. So which among the following is the primary function of tendons? Yes, any doubt? Did somebody raise the hand? Yes, please ask.
Attach muscle to bones. I think, sir.
Okay, answers please inbox. If you have doubt, you please ask. If not, answer you can just inbox.
Yes, sir.
Yes, option C, that is to attach muscle to bones. Suppose we have a bone and we have a muscle. This is a muscle. So, as such, muscle fibers can't directly attach to bones firmly. So, there are other set of soft tissues called tendons and ligaments. So, these tendons, so these tendons are the soft tissues which helping in attaching muscles to the bones. So this even if you have seen some cut sections of body of humans or animals or something, that there you could understand from there is dense colored will be muscle, whereas some lighter color portions will be there, that is tendons. So option Option C, that is attach muscle to bones is the primary function of tendons. Next question. An object weighing 5 kg is accelerating at 2 meter per second square. What is the force acting on the body? It's a simple question. Try to calculate basic Newtonian equation. The object is weighing 5 kg. The acceleration is 2 meter per second. So what is the force acting on the body? Option A, 49.05 Newton. Option B, 10 Newton. Option C, 50 kilogram. Option D, 10 Newton meter. Here the question is simple, but sometimes there will be mixing with the units. So there will be Newton will be there. Some other there will be similar options with mixing up of units or something. So all these things, all these kind of questions will be there. You might simple, you will think it as simple and try to answer in a hurry, but you might accidentally click the wrong option also. So whenever there is some simple question in between some hard questions in exam or something, so that is there to test your presence of mind. So don't be in a hurry. Try to have a second or two to check the options properly, then only click the answers. The equation is F is equal to ma. So here we all know F is equal to ma, and also we will be doing as simply as 5 into 2 is equal to 10 Newton. But the catch, the actual catch is there. I already told you this is a previous year question paper. But what happened is like time pressure and everything will be there. And also the question before this particular question might have been pretty difficult. So once you see this kind of questions, you will feel a relief and try to just click any 10. So 10 is there, 10 Newton is there. You might accidentally click on this 10 Newton meter, then it's gone. So that simple, whenever there is a simple question, it's like you should understand it's a test of your presence of mind. Take a 1 or 2 seconds, try to answer the questions properly. Next question. If an object weighing 10 kg is at rest, what is the net force acting on the object? So the question is, if an object is weighing 10 kg is at rest, then what is the net force acting on the object? Yes, here is the catch. The question was net force. What is the net force acting on the object? So again, this is the link between these two questions. So here object weighing is equal to F is equal to ma. It was easy. We calculated 10 Newton. It was answer. So next question is this. So everybody will first think like F is equal to ma is again the question. And here there is no acceleration. So it is given it is at rest. So gravity might be acting on it. So F is equal to mg. then gravity we can just assume as 9.8 as we always do. Then, but there is approximation. This is an approximation. Then again, if you apply that, you will get the answer 98.1 Newton. That is B. But the answer is wrong because the question was asking net force acting on the body. So when the body is at rest, that is, it is at equilibrium. So the net force acting on it should be zero because this is the force due to gravity. A physical mg is the force due to the action of gravitational force that is acting downwards. But there is something equal and opposite countering it. That's why it is able to be at rest. So please think, if the body was acted upon by this F is equal to mg, then it should have some, that is some 98.1 Newton is acting on 10 kilogram body, then it should either move in direction of that force or it should deform. So it is, the question is not saying that, it is saying it is not moving, that it is at rest. And what is the net force? So when something is at rest, it is an equilibrium. So there is something opposing the force. So that is the reaction forces. So equal and opposite reaction are cancelling each other. So the net force is zero. That is option C. So this is the, whenever you see a simple question, that is most probably this question will try you to do a wrong calculation here. So again, not in NPTEL exams, any kind of exams, these kind of questions will be there. This kind of a coming in the couple. So one question being simple is not that, it is kind of changing your mindset or making think you in a simple way and taking away your presence of mind. Try to answer the question carefully, then only answer. Next question, magnitude of a vector v is equal to 5i plus 2j is given by. So here is a vector v with its components 5i plus 2 times j. What is the magnitude of the vector? That's the question. Options are 5.39, option B 29, option C 7, option D 10. So what is the magnitude of the vector? Try to recall the basic vector mechanics you might have studied in school and try to answer the question. Yes, magnitude of the vector. Yes, the equation is given by so square root of vx square, that is 5 square, plus vy square, that is 2 square. Again, square root of 25 plus 4 is 29 square root. That comes around 5.385 something. So this is the answer. That is option A is the answer, 5.39. But here again the catch is like option B is 29. Sometimes if you are in hurry, you may be doing it in your mind without using pen and paper or calculator or something. You'll be just doing in mind, and you will don't recollect that you have to take a square root of it, and you'll just try to answer it. And even if you are doing it in mind, you can simply uh, assume, not assume, approximate the square root of 29. That is, square root of 25 is 5, and square of 6 is 36. So there should be some value between 5 and 6. So the only option here is option A, 5.39. So now these kind of questions, these are simple questions coming in a back to backs, you can easily answer. But when in actual exam, this will be something sometimes proven to be tricky. Next question, simple question. What is the rate of change of velocity called as? Option A, speed. Option B, acceleration. Option C, momentum. Option D, force. Rate of change of velocity. Quick answer. Yes, acceleration. Yes, option B, acceleration. Okay, moving on to next question. Next question. If a force on an object is doubled, assuming the mass remains constant, then what happens to the acceleration? I'll read again. If the force on an object is doubled, assuming the mass remains constant, then what happens to the acceleration? Option A, it remains the same. Option B, it is halved. Option C, it doubles. Option D, it quadruples. Try to answer the question. Yes, option C, it doubles. Sorry, here option C, doubles. So if anybody has a doubt, let me clear that. Our equation is F is equal to ma. So the question here asks, if the force on object is doubled, that is F becomes 2F and mass remains constant. So the m remains constant. Then what happens to the acceleration? Then A should be 2A. Then only this get balanced. So when the force doubles, acceleration balance when the mass is constant. So our answer is option C, it doubles. Next question. If a person is standing on the ground, the reaction force to their weight is option A, the force of gravity acting on the person. Option B, the force of the ground pushing up on the person. Option C, the friction between person's feet and ground. Option D, the air pressure around the person. So the question is, a person is standing on the ground, and what is the reaction force to their weight? What is the reaction force acting against the weight of a person standing on the ground? Options are: option A, force of gravity acting on the person. Option B, force of the ground pushing up on the person. Option C, friction between person's feet and ground. Option D, air pressure around the person. So this is the ground and this is a person standing on ground. So his weight will be acting downwards. F is equal to mg, and what will be the reaction force against this particular weight? That is the force of the ground pushing upon the person. That is option B. The right answer is force of the ground pushing upon the person. So force of gravity acting on the person itself is their weight. Air pressure don't do much. Friction between person's feet and ground is the one that help us to walk or move. Option C. Next question. The effect of force on a rigid body is the same if options are: option A, the force is moved along any line. Option B, the force is moved along its line of action. Option C, the force is moved along the object's surface. Option D, the force is applied at random angle. So this is again a direct question. What is the effective force on a rigid body if it is the effective force on a rigid body is the same if it satisfies which of the following condition? So direct question from what we have discussed today, that is of principles of transmissibility of force. That is, the force can be moved along its line of action without any consequences. That is option B. The effective force on a rigid body is the same if the force is moved along its line of action, which is the definition of principle of transmissibility. Next question. Which of the following is not typically studied in statics? Option A, motion of a car. Option B, muscle forces in human body. Option C, forces on beams and structures. Option D, normal forces between contacting surfaces. So the question is, which among the following is not typically studied in statics? So the question is a direct question from branching of classical mechanics. Uh, there are different types of mechanics. Uh, there are classical mechanics, rigid body mechanics, deformable body mechanics, fluid mechanics, and there are different types of mechanics. So classical mechanics is split into two, that is statics and dynamics. So if net force, net moment is equal to 0, that is statics. Any case where the net force is equal to 0, we can assume where the net force is equal to 0 or net force and moment equal to 0. All the such cases comes under static, where dynamics are the study of bodies at motion. So if you see here, all three BCD can be uh, assumed to be static. That is, the net force and net moment under acting on it can be assumed to be 0. Whereas the motion of a car is like it is moving from place. It is specified that motion of a car, it is moving. So it is dynamics. It comes under the dynamics branch of mechanics. And again, if you know, there are different branching of dynamics also. This is called kinetics and kinematics. So why I am explaining this is we will be I have explained giving the outline for the weeks. We said there is forward kinematics and inverse kinematics. So uh, 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 these are two branch of dynamics where studying the motion. So if we are not considering the forces, that we are only considering with the movements, rotation or translation, that kind of movements, then such study is called kinematics. Here we don't uh, what deal or kind of calculate forces, but if we are considering what are the forces uh, causing the motion or the force caused by the motion, if such calculations are being done, then it will fall under kinetics. So here force is considered, here force is not considered. So that's the difference. Why I am explaining this here is like we already explained when the dynamic Hartenberg and also motion of linkages, we will be calling it kinematics, forward kinematics and backward kinematics. Sorry, inverse kinematics. Next question. When lifting a weight, the moment arm of the weight relative to the elbow joint is increased if option A, weight is held closer to the body. Option B, the arm is fully extended outward. Option C, the weight is reduced. Option D, the weight is moved faster. The question is asking, when lifting a body, the moment arm of the weight relative to the elbow is increased if option A, the weight is held closer to the body. Option B, the arm is fully extended outward. Option C, the weight is reduced. Option D, the weight is moved faster. Try to answer the question. first of all, what is moment arm? So this is a hinge and this is a link. Then suppose some force is acting somewhere, then the perpendicular distance between the action of force and the hinge or the uh, point is what is called as moment arm. It's also called a lever arm. Is the perpendicular distance between axis of rotation and axis of action of force. So suppose this is moment. So in when lifting a point, lifting a weight, the weight relative to the elbow joint is increased. If what will happen? So elbow joint and the what the perpendicular distance or the axis of rotation is our shoulder. If you are expecting the shoulder, then the when the moment arm will increase, the moment arm will increase when the arm is fully extended outwards. So that is option B. So if the weight is held closer to the body, then the weight will be decreasing. Weight related to the elbow joint will decrease. So our answer is option B. Next question. If the biceps muscle has moment arm of 3.5 centimeter and generates a force of 100 Newton, what is the moment or torque produced by the elbow joint? So even though we have not started discussing about muscles, I hope everybody knows what's the biceps muscle. So the question is, if the bicep muscles has a moment arm of 3.5 centimeter and generates a force of 100 Newton, what is the moment or torque produced at the elbow joint? Options are 3.5 Newton meter, option B 35 Newton meter, option C 350 Newton meter, option D 3500 Newton meter. So the moment equation is M is equal to F into D, or force into perpendicular distance. Moment is equal to force into perpendicular distance, where D is the moment arm. So here force is 100 Newton and moment arm is 3.5 centimeter. You have answered mostly 350 Newton meter, but that is wrong because the devil is in the details. You have to check for the units. Here the moment arm is 3.5 centimeter. So it will be 100 Newton into 0.035 meters. isn't it? Then our answer becomes 3.5 Newton meter, not 350 Newton. So here the unit is in centimeters. And also we were talking about muscles. So muscles can't have 3.5 meter. So answer is option A, 3.5 Newton meter, not 350 Newton meter. Next question. In 2D equilibrium, the moment equation delta mc is equal to 0 can be applied about any point because options are option A, it simplifies the calculation for unknowns. Option B, it ensures that the sum of all forces is 0. Option C, the net moment at any point might be 0 for equilibrium. Option D, it is only valid when forces are parallel. So the question is, in 2D equilibrium, the moment equation sigma mc is equal to 0 can be applied at any point because which of the following condition? Option A, it simplifies the calculation for unknowns. Option B, it ensures that the sum of all forces is 0. Option C, the net moment at any point must be 0 for equilibrium. Option D, it is only valid when forces are parallel. Okay, I can see most of you have answered C. That is, the net moment at any point must be 0 for equilibrium. Yes, and that is true. Sigma mc, if we are taking sigma mc, then the net moment at any point will be 0 for equilibrium. So that's the reason. Option C is the right answer. But I have already told you on the first question or second question itself, you should check whether there is multiple right answer. And option A, that is, it simplifies the calculation for unknowns, because even in 2D equilibrium we can take sigma mx or sigma my. It's not like we can't take, we can take sigma ms and sigma my equilibriums, but sigma mz considerably simplifies the calculations. That's also a reason. So options A and C both are correct. Option A and option C both are correct. Moving on to next question. In a class 2 lever, we have already discussed class 1 lever. So in a class 2 lever, what happens? Option A, the load is located between fulcrum and effort. Option B, the fulcrum is between the effort and load. Option C, it always provides a mechanical advantage. Option D, it never provides a mechanical advantage. Try to answer the question. So the load is located between the fulcrum and the foot. The fulcrum is between the foot and load. It always provides a mechanical advantage. It never provides a mechanical advantage. So for easily remembering the levers, class levers, we have already uh, said that in class 1 lever, fulcrum is in the middle. So that is this option B. So option B here is wrong. For class 1, fulcrum is in the middle. So in class 2, load is in the middle. So it can uh, effort and fulcrum can take in this side, but load is in the middle. And third one is like effort in the middle. So if you keep this in mind, FLE, that is fulcrum in the middle. Second one, load in the middle. Third one, effort in the middle. So here the load is located between fulcrum and effort. Option A is the right answer. But here again there is another right option, that is option C. It always provides a mechanical advantage. So the mechanical advantage for class 2 levers is always greater than 1. So that's a condition. So here again option A and option C is correct. So that's all for today. If you guys have any doubts, please ask. If not, you are free to leave. The next section will be on next Monday, 7 to 9. Thank you guys. Thank you.